All right, there we go. Let me begin with I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to bless our work today, Lord. In your name I pray. Amen. So I had you guys do some examples, set up some examples on the board here. And so let me evaluate the success. So here we go. Example 1, integral from 3 to infinity of e to the minus x dx. Okay. Limit as a goes to infinity. Sure. This is right, but nothing wrong here. But you could just do, all I was looking for here was limit, let's say t goes to infinity of the integral from 3 to t of e to the minus x dx. Like that. That's all you gotta do. Right? Hey, while we're at it, let's calculate this one. What we got? Can you do that integral? I think you can. That gives us minus e to the minus t plus e to the minus 3, right? What happens as t goes to infinity of e to the minus t? So this guy is gone, right? And we're just left with e to the minus 3. So this integral converges to e to the minus 3. Okay. Example 2, we have very good. So what we've written is good. I'll just write it again here. Limit as a goes to infinity of the integral from pi to a cosine of x dx, right? So if you are going to write equals down here, maybe write equals up here and like a connecting or something. Yeah. So I'll actually do this integral since it's not too bad. What we got? What's the integral of cosine? Sine, right? So we're looking at sine of a minus the sine of pi. What's the sine of pi? It's 0, right? So what's the limit as a goes to infinity of sine of a? It does not exist, right? So this, we'd say this integral does not exist. And as I was telling one of you guys after class last time, like, does not exist is just short for a longer sentence, which is to say, does not exist as a real number, all right? We cannot meaningfully assign a real number to describe the signed area under the graph of y equals cosine x from pi to infinity, right? I mean, I can even graph that, you know? Forever and ever, like what's the signed area under that? You know? As you go on out, it's oscillating between having negative total or a positive total as you go from cycle to cycle, you know? Okay, next up, example 3, integral from 0 to infinity of x squared e to the minus x. I have the limit as a goes to infinity of the integral from 0 to a of x squared e to the minus x dx. We have a winner. Yes, that is correct. I cannot squeeze the solution to that one into this little box. We'll come back to this one, okay? Very good, very good. Here we have the integral of from 0 to 6 of dx over x squared minus 4. And it looks like you guys you've approached 2 from the left and then from the right, right? So you split the integral up. So the question that you might have is x squared minus 4 is what? X plus 2 times x minus 2, right? So this one is troublesome. That's trouble because when we put in x equals to 2, that's 0, right? So we have division by 0 at 2, but the minus 2 is harmless, right? That's outside 0 to 6, so that doesn't cause us any pause. If the integral had been from like minus 4 to 4, you would have had to break it up into 4 separate integrals, each with its own limiting process, right? Very good. Integral 0 to pi over 2 tangent x dx. So we have the limit. I think it's right, but I'm going to, this is correct, I'm just making it in bigger font is all, okay? So, come on, youngsters. Limit as b goes to pi over 2 from the left, integral from 0 to b of the tangent of x dx. I'll just put some, those parentheses aren't technically necessary, but I just like parentheses. What's the integral of tangent? The integral of tangent is not secant squared. Nope, 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 nope. It's ln absolute value secant x. That'll do. So we look at the natural log of the secant of b minus the natural log of the secant of 0. I don't need the absolute value y because we're in a positive range, right? So the absolute value just simplifies to the value. And of course, secant of 0 is 1, right? Secant of 0 being 1, because 1 over cosine of 0 is 1 over 1, which is 1. But natural log of 1 is 0. So this piece here drops out. All right. And the first one, though, what's that? I mean, I'll rewrite it one more step. This is maybe make it more familiar. Limit as b goes to pi over 2 from the left of the natural log of 1 over cosine, right? What happens to cosine as we approach pi over 2 from the left? 0, yeah, but what kind of 0? So this is cosine, this is pi over 2, right? We're feeding it a point from the left, right? So b is like in here, right? So we're feeding very small positive values into the, well, excuse me. Yes, cosine, this takes small positive values. So this reciprocal here is what? Something very, very large and positive, right? So we're essentially feeding infinity into the natural log. What's the natural log of something very, very large? Or we could say log of infinity is also infinity, right? In the limiting sense. So in short, this is infinity. Okay. Next up here, we have integral from minus infinity to 3 of e to the minus x cosine x dx. And, oh, I'm going to have to disagree with this one. So here we're just looking at the limit as, let's say, t goes to minus infinity, the integral from t to 3 of e to the minus x cosine of x dx. All right? There's no need to break it. I'm not sure what's going on here. Well, anyway. That one needs some work. All right. So, but that's okay. I mean, we just started this yesterday, right? It's understandable if you don't know it yet, but something to work on. So that's the thing we'd have to calculate. Now, we'll come back to this one because, again, I can't do the antiderivative here in my little box. All right? So mental note, come back to this one. We'll come back to that one in a bit. Next up here, example 7. I'll do example 11 next. So 711. The integral from minus infinity to infinity of dx over x squared, we have limit see, not quite. Not quite. It's worse than that. It's worse than that. So what you want is, I'll write it symbolically, and then I'll put limits in, okay? Integral from minus infinity to 0 of dx over x squared. Curses, so here's kind of what you had, but this would still not quite fit the bill. I mean, I want you to set it up in terms of limiting processes. We're not there yet. So this would have to be broken somewhere. Let's break it at -1. And what I'm finally writing is a sum of 4 improper integrals. Each one can be written in terms of a single limiting process, all right? Which I think I'm going to need my full. All right, so we have the limit as, let's say, a goes to minus infinity of the integral from a to -1 of dx over x squared, plus the limit as, let's say, b goes to 0 from the left of the integral from -1 to 0, b rather, not 0, but b, dx over x squared, something like that, plus the limit as a goes to 0 from the right of the integral. And let me just take a step back here, guys, and make my first one an s. Say s goes to minus infinity, and I'll put an s down here. All right. Getting back to the third one, integral a goes to 0 from the right, integral from a to 1 of dx over x squared. Finally, plus the limit as t goes to infinity, integral from 1 to t of dx over x squared. Yeah.
So, how'd you pick the one exactly? Are you just picking like a number between -10 and 0?
Yep. Exactly. The one is not the one, or the -1 and the 1 here are up for grabs. Like, it would not change anything. It would be an equally correct answer if, instead of putting -1, I'd put -2 here and -2 here. And I could put 11 and 11. Wouldn't change a thing. There's an infinite number of choices of where to split the doubly improper integral like that, yeah. It's a theorem that it doesn't matter. So why did I use 1 and -1? Just, yeah, if I actually calculate things, 1 is easy to plug in, right? Okay, so there's example 11. So this is kind of embarrassingly easy after that one, isn't it? So integral from 1 to a. Oh, no. No. It's no bueno. This should not be x. We need to have a goes to infinity here, right? So I will fix. Limit a goes to infinity, integral from 1 to a of dx over x squared, right? All right. And I'll actually calculate this one because I got room. So what's the integral of 1 over x squared? It's -1 over x, right? So by fundamental theorem of calculus part 2, I have -1 over a minus a -1 over 1. Of course, the 1 over a goes to what as a goes to infinity? Goes to 0, right? And so the answer is 1. The example 11, if you work out the details, it does not converge. And the reason for it is that the middle two integrals blow up. The tail ends are fine. Like this, if you wanted to picture, this is the volcano function, right? And so what I just calculated in example 7 is the area from 1 out to infinity, this guy. And I showed that area is 1. And you know what? If I go back to my minus 1, before I made the response to the question in the back there, you could also calculate the area by very similar calculation, the integral from minus infinity to minus 1 of dx over x squared. Guess what? You could also show that that's 1. All right? However, when you actually go through the details of these two guys in the middle, you're going to get that it blows up because you've got like a minus 1 over x, and you're going to take you end up with like a minus 1 over b as b goes to 0, and that just blows up. So these actually both will work out to infinity when you go through the details, which I can't fit in here. So example 11, actually, when we work it out, despite the fact that we have finite sort of bookends, it doesn't matter. The middle of the integral blows up. So the net result is that integral diverges to infinity. Example 11. All right, example 8. What's the trouble here? 0, right. Where is there 0? Oh, at 0. We have division by 0 at 0, right? Because cost of 0 is 1. So we have cost of 0 minus 1, which is 1 minus 1, which is 0. That's troubling. Fortunately, 0 is an endpoint, so we only need one limit. Limit as a goes to 0 from the right. Integral from a to 2 of dx over cosh x minus 1. Can you guys do that integral? Maybe we'll try, but let me focus on finishing the examples here before I get into that. Next up, we have, so that's the setup, all right. The integral from 0 to 1 of dx over, quiet. It's probably nothing of consequence either. Shut up. This is my brother's reminded me something, yes. Actually, it's relevant to the class, this email, as we'll see in a little bit. But, all right, next up, integral 0 to 1 of x squared minus 3x plus 2. Side note, x squared minus 3x plus 2 factors as x minus 1 times x minus 2, right? So we have division by 0 at x equals 1 and x equals to 2 for the integrand, right? But does division by 0 at x equals to 2 matter to us here? It does not, right? Because the integral is from 0 to 1. But what does matter is that we have, that x equals 1, that is a point of contention, isn't it? So there we need to limit, as you have said, limit as a goes to 1 of the integral from, what? What is the meaning of this? See, these are the kinds of questions you have to resolve before you can teach Calculus 2. Because when you're grading a test, you'll be faced with questions such as this. Is that a 0? Is that an A? If it's an A, there's much more partial credit. Right? Let's be optimistic. This was an A. This was an A. That was an A. It was an A. Now, even so, we still have a problem here. Can you guys tell me what is the problem? Oh. Okay, so I've interpreted it wrong. That was a 0. And if you look really, really hard, you can see that this was an A. So with that, we're almost good to go because we still have one other thing to fix here. Yeah, it's one from the left. So the idea here, guys, is that there's what are the asymptotes at 1, asymptotes at 2. The thing we're integrating. Let's see here. I think it looks something like this. Whee! I don't know. I think it's something like this. Is that right? What happens if I plug 1.5 into this thing? Oh, I think it actually does like this. And then, I think the graph looks like this if I had to. I mean, I'd have to study it more carefully to be sure, but I think that's the global graph of the integrand, something like that. It's got, yep.
How do you know what to do it from the left or the right? Like, you know how earlier you said, like, with from the left, like, how did you decide that one from the right?
Well, that's I was working on drawing a picture to try to explain that further. Actually, that's what I'm doing right now. So your question is good. So this integral, right, is the signed area from 0, right, to 1. But of course, we can't do that because 1 is where the function is not defined, right? So the meaning of this is improper. And so what we do is we kind of just, here's an a, right? And so we're letting this a go that direction, right? And so if you think about that, that is a is approaching 1 from the left. Our notation for that is a approaches 1 with an upper minus. Does that make sense? So I mean, you have to think about geometrically, are you filling out an integration region going to the left, or if it's the lower bound, it goes to the right. Oh, hey, while we're on the topic, you guys, we talked about numerical methods a little bit, right? Not a lot, but a little bit in here. We talked about left point, right point, midpoint, Simpson's, trapezoid, right? So if you think about the left, the right, and the midpoint rule, which one would be the smart one to use for a numerical method if maybe your model could possibly be divergent? Like, what if you're doing an integral that maybe it's an improper integral? If you wanted to numerically calculate that, what would be the trouble with the left and the right endpoint rules? If you think about it, the setup of the left and the right endpoint rules, it uses what? It uses endpoints. So if the endpoint of your integration domain is a place where the function's not even defined, left and right endpoint rules are just going to blow up in your face, right? They're not going to even make sense. But the midpoint rule never actually uses an endpoint to the integration domain. So midpoint actually becomes a better method for calculating divergent integrals, in the sense that if the apparently divergent, if the improper integral actually converges, the midpoint rule has a better chance of actually detecting it. Anyway, that's the sort of thing you probably should be talking about in Math 352 here, which was what I was advertising to you guys earlier. Other good choices, by the way. 331, which is complex analysis. So people are asking me what I would recommend for mechanical engineering's missing math course. You guys have like one, if you're going to add the math minor, so you need like one extra course, right? You get your Calc 1, 2, 3 differential equations, and then you get one more course. Because of course we would never take math courses outside our GCP, right? That would be crazy. I'm joking. So complex analysis is a good choice, or another choice would be 332, which is advanced calculus. This is just odd fall semesters. So for you guys, since you're in Calc 2 right now, right? To take advanced calculus in the next fall semester, that would mean that you'd need to do Calc 3 over the summer. right? Which is not impossible, but would be hard to do here, as we don't offer Calculus 3 online. But if you're interested in this at the end of the semester, talk to me, all right? There is a way to do Calc 3 in the summer here that has been done by students. I have had a student take Calculus 2 with me this semester, do Calculus 3 over the summer, and then take advanced calculus with me in the fall. This has been done. That student now has a postdoc at Duke. So he's a good student. All right, next up. Anyway, these are courses I recommend for the math minor if you're a Mechie. These are interesting further calculus, all right? Both of these. If you're going to graduate school in engineering, either one of those would make you a stronger student going forward. There are other choices, but I won't mention those because I don't care. All right. Sorry, I'll be bad. What do we got here? Integral. Those other professors can advertise those to you. I think this is correct. I will recreate the answer in a larger font. Equals limit as, let's say, s goes to minus infinity, the integral from s to 1. Why did we put 1 there? Because 1 is easy, right? Because 1 is the loneliest number, so it should make it feel better. So we use it. There we go. See, 1 isn't lonely anymore. All right. What have I done? Oh, good grief. Yeah, don't do that. Oh, and don't do that. Golly. All right. So, yep.
What's the difference between doing that for 10 and doing all of that for 11?
There is a very significant difference. 1 plus x to the 4th equals to 0. When? What's the solution to this? No, let's talk about this. Don't. This is an important question to ask. How are we deciding where the integrals are misbehaving? It's where we have division by 0 predominantly, right? That's the usual thing that we're facing. And so here, the thing is that has no solutions, no real solutions, right? All the solutions to that are complex. There are 4 of them. But, we keep it real in here. Where was I? In contrast, this, of course, 0. 0 is the solution of x squared, right? That's why those are very different examples. One of those is much easier for me to grade on the test than the other, but one of them I feel honor bound to put on the test. I mean, I should put something like this on the test. Putting something like this on the test is very revealing. If you really set that up right, it pretty much means you understand what we're doing. That has pretty much everything in it. Example 11 has pretty much everything in it from a setup perspective. So if you understand these 11 examples, guess what? Great. I mean, that means you're well on your way towards being able to do these. Now, of course, the next step in our evolution, maturation. Evolution has a meaning that predates, the godless philosophy of 19th century natural philosophers. It used to be a word we just used in physics. We talk about time evolution. This just means things going forward in time. It's not a. We should reclaim the word. All right. Have any of you guys been to the Ark? Yeah, the one in Kentucky. It's like I like his Reclaim the Rainbow initiative. Have you seen these? No? All right. Okay. Oh yes, example 3. Let's do it. So let's do it. So to do this one, what I like to do, if my integral is a little bit complicated, my preference is to just work out work out the antiderivative first and then apply that to the limiting procedure, all right? So I break it into two pieces. First of all, do this integral. This is dv1, this is u1, so I get what? Minus x squared e to the minus x plus the integral of 2x e to the minus x dx. This is my dv2, this is my u2, so I get minus x squared e to the minus x plus parentheses minus 2x e to the minus x plus, excuse me, the integral of 2 e to the minus x dx, if I haven't made a stupid mistake yet. And so this is what? Plus a constant, right? Plus a constant. So I'm going to repackage this a little bit. This is really minus e to the minus x times minus x squared, times rather x squared. Have I lost a minus? Well, we could check our answer, right? It just feels weird. I feel like I should have a plus minus here. Something doesn't feel right. I'm going to let you guys look at my work and see if you can see if you can verify this or tell me where my error is while I'm erasing some things. Well, we'll come back to that. If you're uncertain of your answer, what's one thing you can do to check? Take the derivative, right? What happens if I take the derivative? Let me call this thing f. What's df dx? We have e to the minus x times x squared plus 2x plus 2 minus e to the minus x times 2x plus 2 by the product rule. Right? And what happens there is this 2x cancels that 2x, and this 2 cancels that 2, and it just leaves me this, which is that. Hey, I didn't make a mistake. What do you know? Does that make sense? I mean, I think it's worth, if you have time, a second to check your work, right? Okay, with that in hand, now we can calculate the integral, say from, from 0 to infinity of x squared e to the minus x dx. This is the limit as t goes to infinity, the integral from 0 to t of x squared e to the minus x dx. All right, and so that's the limit as t goes to infinity of f of t minus f of 0. I put this in between step in here just to emphasize the logic of what I'm doing, okay? I don't always write that down, but I think it's helpful. I mean, that's what I'm doing. I'm taking this antiderivative, I'm plugging in t, I'm taking the difference at 0. What happens when what is f of 0 here? Right? f of 0 is just minus 2, so minus f of 0 is plus 2. So we can rewrite this as 2 plus the limit as t goes to infinity of f of t, which is what? Minus e to the minus t times t squared plus 2t plus 2. I'm using a limit law here, right? When I pull the 2 out like that, I'm assuming that the subsequent limit exists. And if it does, then the limit of the sum is the sum of the limits. However, if the thing I just wrote limiting process for ends up diverging, we also understand that 2 plus a divergent integral is divergent. So there's really nothing lost in pulling out the 2 here, as I did. All right, so what is this? Minus the limit as t goes to infinity of, what we got? I say what we have is t squared plus 2t plus 2 divided by e to the t. And the reason I did that is in the above, we're looking at something that's indeterminate, right? But it's e to the minus infinity, which is like a 0, something tending to 0, and then the polynomial, which is, of course, tending to infinity. So we have like a 0 times infinity type indeterminacy in the above calculation by moving e to the minus t downstairs, right, as you guys did in like example 1 that you had written up here a while ago. Then this is nice, because now we're looking at infinity over infinity, right? So I can apply L'Hopital's rule. And what does that give me? It gives me 2t plus 2 over e to the t, right? L'Hopital's rule. And then, still got infinity over infinity, right? So again, applying L'Hopital's rule, differentiate the top, differentiate the bottom, and we get 2 over e to the t, at which point we have removed the indeterminacy. L'Hopital's rule has served us well. It has revealed that this limit that was left over actually tends to 0, and the answer is 2. So this integral, the integral from 0 to infinity of x squared e to the minus x, converges to 2. Yep.
Wait, how'd you get to 2 in the first place? Like outside of the limit, like.
F of minus f of 0 is minus a minus 2, which is 2. Yeah. Es bueno. Muy bueno. Es muy bueno. All right, so I think it was example 3. I can't remember. Example 6, 7, whatever it was. Anyway, example. Let's work out the integral of, let's say, e to the minus, we'll do e to the minus x cosine of, say, 4x dx, all right? So this is my dv, this is my u. I get minus e to the minus x times 1/4 sine 4x plus 1/4 integral of sine 4x, oh, snake, e to the minus x, sine of 4x dx, make this my dv2, my u2, minus 1/4 cosine 4x e to the minus x, and then minus the integral of minus 1/4 cosine 4x du is minus e to the minus x dx. there are 1, 2, 3 minuses on that last term. So it looks like we've got 1/4 e to the minus x, parentheses, I'll put a minus up front there, minus 1/4 e to the minus x sine 4x plus 1/4 cosine 4x. And then this guy, 1/4 minus 1 over 16 integral of e to the minus x cosine 4x dx. Okay, so as usual song and dance, this is I. What we're looking at here is minus I over 16. So therefore, the integral of e to the minus x cosine of 4x dx is equal to, what's 1 plus 1/16? 17/16, so then we multiply, we have 16 over 17 minus 1/4 e to the minus x sine 4x plus 1/4 cosine 4x plus a constant. Which I suppose I could clean up a little bit. Integral that gives me what? Minus 4 over 17 e to the minus x times the sine of 4x plus 1/4 the cosine of 4x plus a constant. All right, nothing improper here, right? You're like, well, that's debatable. Any questions? I mean, this is test 1 stuff, but it still matters, right, as long as we're doing improper integrals. So I think I had, or I could ask the question, what's the integral, say, from, 0 to infinity of e to the minus x cosine of 4x dx? Then that would be what? Limit as t goes to infinity of minus 4 over 17 e to the minus t sine of 4t plus 1/4 cosine of 4t plus 4 over 17 e to the 0 sine of 4 times, sine of 0 plus 1/4 cosine of 0. Close limiting process over here. Now, the limit of, so we need to talk about some things here. Well, let's make a step. This is equal to, this piece over here is easy enough to understand. That's sine of 0 is 0, e to the 0 is 1, cosine of 0 is 1. So in short, we get 1/17 for that. Right? But then plus the limit as t goes to infinity of minus 4/17 e to the minus t sine of 4t plus 1/4 cosine of 4t. Does that make sense? E to the 0 is 1, sine of 0 is 0, cosine of 0 is 1. So the term underlined in red simplifies to 4/17 times 1, parentheses 1 plus 1/4. The 4's cancel. It leaves us with 1/17. The question then is, what on earth we do? What do we do with this piece here? How do I understand that? See, we can't just use limit laws, right? Because you guys tell me, what's the limit as t goes to infinity of sine t of sine 4t plus 1/4 What's that limit? It's indeterminate, right? That does not exist. So wait a minute, if that doesn't exist, then how can we calculate what's underlined in the green squiggle? Because this is an indeterminate limit times something which does what? What's e to the minus t do as t goes to infinity? This is going to 0, right? So the pattern here is something that's going to 0 times something that's indeterminate. So how do we calculate this kind of limit carefully? What we do is we notice that sine 4t plus 1/4 cosine 4t is bounded. Can you tell me a lower, upper lower bound for that expression? Let's be greedy. What's the biggest cosine and sine can ever be? They can both be 1, right? That's not actually, that can't actually be achieved at a single time, but let's just be greedy. So just biggest this could possibly conceivably be, and it never can actually do this, but this is actually, I could confidently erase the equality there because sine and cosine are never both 1 at the same time. And likewise, my point is we don't have to think hard about this. This is definitely a bounded expression, right? And so you have this inequality. This is for all time, right? But certainly for, what is it? 0, t greater than 0, which is where the integration's about, right? I mean, that's actually true for all time. Then what can you do this? You can say, well, minus 5/4 e to the minus t is less than or equal to e to the minus t times sine of 4t plus 1/4 cosine of 4t, right? Less than or equal to 5/4, I'll put the equals back in just because it's fun, 5/4 e to the minus t.
How'd you get the -5 and the -4 for your bounds?
1 plus 1/4 is 5/4.
So you just added the two coefficients.
Yeah. If we wanted to, we could slog through the trigonometry. There does, in fact, exist. It's possible. It can be done. You electrical engineers should know how to do this because it's the kind of thing you want to do with phasors. There exists an A, an amplitude, a phase angle, delta. You can pick an A and you can pick a delta to make that equality happen. Because you're adding two sinusoids at the same frequency, they can be written by principle of superposition as a single sinusoid with a particular amplitude and a particular phase angle. And with that, I could actually bound this, I could find optimal bounds between plus or minus an A. But I don't want to go through all that because I'm just trying to show this thing is 0. And I think we have everything we need, see, because now we have that this is bounded by these two things. What happens with these two things as t goes to infinity? Right. So this goes to 0, and that goes to 0 as t goes to infinity. Thus, by squeeze theorem, we have that the limit as t goes to infinity of e to the minus t sine 4t plus 1/4 cosine 4t equal to 0. Right? So all of this just to carefully explain to you that the thing with the underlined green squiggle goes to 0. And so the integral converges to 1 over 1/17. Yeah.
We're like doing this for the test to like go from like the second to last line to last line. You need to mention that we like use this piece.
Well, if the instructions say to calculate the improper integral, carefully explaining why any limits work out as they do, then yeah. Depends on the instructions. Now, would you get significant partial credit if you just had the intuition that that went to 0 and you didn't explain why with squeeze theorem? Yeah, of course. Right? But the best answer includes the details. Yeah. So let's work on intuition. All right? See, because the next thing that you want to work on is the comparison theorem. All right? So what's the comparison theorem say? It says if we have, f of x less than or equal to g of x, let's say for, I don't know, a less than or equal to x, more to the point, x greater than or equal to a, then the integral of f of x dx from a to infinity will be less than or equal to the integral from a to infinity of g of x dx. Provided both exist. Actually, it's more than that. The comparison theorem is more than that, all right? Furthermore, if we had 0 is less than or equal to f of x, is less than or equal to g of x, for x greater than or equal to a, and the integral from a to infinity of g of x dx converges, all right, then the integral from a to infinity of f of x dx converges. Indeed, we can in fact say that 0 is less than the integral from a to infinity of f of x dx, and that's less than or equal to the integral from a to infinity of g of x dx. So it's very intuitive what I'm saying. What I'm saying is if you can prove that the integral of a larger function converges, right? And if the smaller function can't be negative, right? If it has to be between 0 and the larger function, then the fact that the area under the larger function exists and is bounded means that the area under the smaller function also exists and is bounded. This is a very intuitive theorem. It's not surprising at all, really. So here's a picture of what's going on. So here's y equals g of x. And I'm assuming that the graph of f of x is below it, right? I mean, it could touch on it certain places, right? But it's generally below. And so I'm saying that the area under the red has to be less than the area under the blue. So this is the sort of positive aspect of the theorem in terms of convergence. What's the flip side of this? What if we knew that the integral under the red diverged? Right? What if again we have, I'll stick with the same lettering, 0 less than or equal to f of x, less than or equal to g of x, and the integral from, a to infinity of f of x dx diverges, then the integral from a to infinity of g of x dx diverges. So if the integral of a smaller function blows up, certainly the integral of a larger function is also going to blow up. This is not especially surprising, but this is a theorem we have. This is the so-called comparison theorem. All right. There are also comparison theorems for other kinds of integrals, like minus infinity to a constant, or the other types of improper integrals we've talked about. This is a general kind of theorem we can write for any of the integrals we've looked at of real valued functions. All right. I'm just focusing my attention on the case of a to infinity because it's the most common case that I ask about and you face. All right. So in order to make this comparison theorem really interesting, we need something to compare to, right? And one thing that's nice to compare to is the following result. Integral from 1 to infinity of, dx over x to the p equals what? Limit as t goes to infinity, how's it go? Integral from 1 to t d, I'll rewrite it. That's x to the minus p, right? Sound good? So you know the song and dance. Here we go. Limit t goes to infinity. We integrate x to the minus p. We get what? X to the minus p plus 1, right? Over minus p plus 1. Evaluate that from 1 to t. And so that's what? Limit as t goes to infinity of 1 over 1 minus p times what? Times t to the 1 minus p minus 1. What I wrote doesn't even make sense if something is true about p. What do we need to suppose from the start of this? P is what? Yeah, p is not equal to 1. P equals to 1 is an oddball here, isn't it? But p not equal to 1, everything I wrote just wrote makes sense. And what happens with this limit? Here's what happens. We get infinity if 1 minus p is greater than 0. All right? And otherwise, right, we get 1 over p minus 1 if 1 minus p is less than 0. Because t to a positive power, right? T to a positive power as t goes to infinity diverges. But t to a negative power is like 1 over t to a positive power, which goes to 0. So the first term there, the t to the 1 minus p, either goes to infinity or it goes to